Hi boys and girls, welcome to a new IB physics video. In this video, once again, I will go through all the questions in modeling a gas on chapter 3.2. We can find on your textbook page 140 to 141. As usual, before we start, we will look into the study guide from IBO and make sure we have gone through everything. So the first thing is I want to look at the equations here. There are four. The first one is regarding the pressure equal force over area, which I actually find is a bit weird to put such equation in this chapter. But anyway, you have chance to use this in the coming questions. The second one is pretty essential, which is the conversion between numbers of molecule, exact numbers of molecules into or go back to the how many moles of the molecules there are. So usually you work with 6.02 times 10 to the power 23. As you know, this is the numbers of molecule in 1 mole. The third one is regarding the ideal gas law, PV equals nRT. If I told you before, I'm sure you learned this in IGCSE as well, although it was not included in the syllabus. And now this time you are going to use this in the calculation. For the last one is extremely new to you probably, and we will talk about that later on and make sure you have tried this kind of question. Apart from the calculation here, I want to point out one more thing which you should pay attention to as well, which is the difference between real gas and ideal gas, which I'll be talking about this in the next slide. Here are the 6 assumptions that we made for ideal gases, and of course which not all the real gases will be very similar to these assumptions. And you may wonder, why would we need that many of assumptions in the ideal gases? And the main reason is actually just now there is the equation of average random kinetic energy, which is 3 over 2 Boltzmann constant times T. You should try to spend some time to prove this equation if you didn't in the lesson, and through the process you try to derive this equation, you will understand why we all need all these assumptions here. So let me quickly go through some of them to you. So for the first one is basically we assume the molecules are basically having infinite small volume, which is tends to 0. For the second one is very simple, obeying law of mechanics, physics, momentum. And the third one is talking about there's no forces between molecules. That means when the molecules are inside the container here, the molecule and molecule themselves, they would not collide each other. What they do individually just to collide with the wall of the container itself, but not each of the other air molecules, gas molecule. And for the fourth one, duration is negatable. So what it means is a momentum, there are impact time, which is F times delta T equal to delta P. And here we may negate the impact time when the particles are colliding on the wall. And the second last is considering the collision is elastic. So that means the Ke is completely conserved and there's no Ke loss during the motion. And lastly is talking about the movement are all random. For the first question is extremely easy. I think the main idea is to look into the unit. For this one, I will prefer to write the unit out so that I can see clearly and understand easily and find the answers correctly. Next question is extremely similar, so I'll show you the steps. The third one is again very easy. For the fraction at the top is how many molecules you have. For the bottom is how many molecules in 1 mole. And therefore the answer is 3.3 mole in total. The next question, the keywords in the question is as many molecules as the other one. So basically, for these two elements, whatever it is, they will have the same amount of molecules as what you want to do. And therefore, the numbers of molecules is, of course, could be calculated by the mass over the molar mass. And therefore, here is the answer. For the next question is a very typical one using the ideal gas law. Usually what I would be doing is I'll write down the variables that you know and how do they change in a very clear way so that you won't mix them up. You may want to follow my format here. And after that, I will consider to take a reference of the ideal gas law here, PV equals nRT, and therefore I can clearly see that comparing with the information I got, I can rearrange the equation so that it's P over T here, and while the other parts, which include N and R and also the V, which are all constants in this question, and therefore I can construct easily that P1 over T1 equal P2 over T2 over here. So you don't need to kind of memorize the equation. You know there are 3 gas law in your textbook, but I don't think you need to memorize them. Just use this way to do, and you always get it correct. One more thing you need to pay attention to is for the ideal gas law, for the temperature, you should always put them in Kelvin scale. And therefore, here, since it was degrees Celsius, so plus 273. And you should be able to find the unit, the answer at last. Next question is again extremely similar to the previous one. Again, the first step is writing down the change and the information that you know. Consider the ideal gas law again, and this time you know PV is a constant. So very simply, you just put PV, P1 V1 equal P2 times V2, and therefore you find the answers for V2, which is the unknown. Next question is slightly harder. So first of all, again, what you want to do at the beginning is to write down the ideal gas law. You may want to check all the information if you have already given from the question. So here's a checklist. For the P, of course you don't know because it's the questions itself. For V, you can find it here from the question. And for R is something that you can find on your data booklet, which is a constant number, of course. And the last one is the temperature, 20 degrees Celsius here. So you are also given the temperature as well. In order to find the pressure, of course, you can't just let the equation having 2 unknown, and therefore you must firstly find the numbers of mole of the gases here, which is the helium. And by saying that, and you also notice in the question here, I did not circle 12 kg, so that means 12 kg is something that you can use as well. And therefore, simply by applying the molar mass, you can find how many moles there are. But pay attention that since the unit is in kg from the question, and therefore you need to change it back to gram so that it matches with the molar mass, 4 gram per mole. Remember, for molar mass is always in gram. Well, I don't really know what I think is the tradition from the chemist. Anyway, and since now you can get the numbers of mole, and you can proceed on substitute all the numbers. So again, substitute all into the equation and you'll find the answer at last. Next question, it looks a bit messy, but I'll explain to you how one by one. So the first step is over here, that from the question you are told that it is 4.00 ATM, which I think you have seen it before. Well, I'm sure you have seen it before in IGCSE physics. And in case you don't remember what's the ratio of that and how you convert it back to Pascal, then here is the answer and the display from the Google, well, which is reliable. In the questions calculation here, I will take it as 10 to the power 5 Pascal. Anyway, so now is a good time to check the ideal gas law again. PV equals nRT, and we already got P, and for the V is over here, which is already done, and R again is a constant. For temperature is 20 degrees Celsius. So we are good to go to determine the mass of carbon dioxide if we know the numbers of mole of the carbon dioxide. So basically, again, sub it all here so that you find the numbers of mole is 1.97 mole. And the next part is more like the chemistry. I don't know why we need to do the chemist job, which is measuring, well, not measuring, but calculating the molar mass. And you know this is CO2, and therefore carbon is 12, and one oxygen atom is 16. In case you don't know, just Google it. Actually, I don't remember as well. I did search it on Google. So anyway, at last you should be able to find the answer as 68.7 gram. If you use this conversion as 101325 Pascal, you should be able to find the answers as the answer key of your textbook, which is 87.9 gram. Next question is slightly long but not very difficult, so make sure you follow me. The first step again is to write down all the things you know, which I put a square here. For volume is something that you know from the question, I put it here, and then after that is a pressure, initial pressure, I put it here, and then the initial temperature, I put it here. And it said the flask will lose the molecules at the rate of blah 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 per second. So here is the expression in terms of the maths equation. I don't really know if it is useful, I just put it down first. And it said how long would it be to get the pressure to be the half of its original. So I'll put you know, this is just for reference, right? You know, it's 2.50. I'm just being lazy here. And it tells you that assume the temperature of the air remain constant during this time. So therefore the temperature will also be a constant. For the volume, although the question did not say that, but you should also know it's a constant because it's a flask. And therefore you should not, I mean, the flask should not be collapsing or expanding because normally it's made of glass. And therefore you can apply the ideal gas law again, and this time you may want to rearrange the terms so that you can put all the variables, which is pressure and the numbers of mole here, so that the other parts of the equation on the other side, which is RT over V here, will be a constant. Therefore you can construct a new equation, which I don't even think your textbook mentioned about it. So it's more about flexibility and how you apply the ideal gas law than, you know, try to memorize all these three gas law by yourself. So now you can get P1 over N1 equal P2 over N2, and therefore if you apply the equation, you find out, oh, N1 should actually be the double of N2, or you may simply say N2 should be half. That means it leak half of the original numbers of gas particles. So in that case, so that means if the M1 should be half, then of course you want to find the M1 first. So simply you use ideal gas law again, you apply everything that you know for the initial condition, and therefore you can find N1. Initially, you will have 0.0602 mole, and therefore N2 simply divide by 2, you find 0.0301 mole over here. The last part is a bit unusual to you, but very simply you can write that the delta N, which is change of molecules over time, which is very sensible, the speed of how fast it leak, will be 3 times 10 to the power 19 over here. I put a negative because it's, you are losing molecules, but anyway, it doesn't really affect your calculation. At last, since you know the N is what you want, you can eventually find the time, which is 4604 seconds, and convert to minute, that will be 10.1 minutes. Next question is probably the easiest question, which requires no calculation, and here it is. So you can see the color code here. For the red one, what you're gonna do is every time I will write the ideal gas law and see what are the changes. So since PV equals nRT and nRT are constant, therefore if the question asks you to double the volume, that means the pressure will be half, and therefore the red dot is over here. While for the part B, volume doubles, so what you gotta do is write the equation again. The others are the constant, and therefore the temperature will be double as well. And therefore you can see that compared with the original dot, the new blue dot should be here. But of course, for the temperature here is not shown. I mean, if you look at the y-axis, is talking about the pressure, right? So the temperature is actually shown by the area that it covers. So you may simply think how much area it covers, which kind of represent the temperature. Well, not completely, but it's proportional to. For part C, it asks you to halve the pressure and constant the volume, and therefore the temperature will be lower, and well, you just follow what they say, and you can see that the area is diminished again, and that means the temperature is lower. Next question is a very, very typical question that I actually pretty like it. So first of all, what you're gonna do is to understand the question. So what you do is you have two kind of different ideal gases here, and they have different volume. Notice that this is a volume and this is a volume 6 and 3 dm cube for each side, and they have different pressure and of course different numbers of molecules. And what they do is there will be the question would say the valves will be open and the temperature stay the same, and guess what, after you open the valve, the pressure on each side must be the same. So P1, well, actually it's basically a one space already, so the pressure must be the same. Otherwise, the gases would still be moving from one side to the other side if the pressure are not equalized. Very simple, huh? So what you're gonna do is, firstly, what I did was to change 1 dm cube into meter cube because we want to follow the SI unit. And in case you don't know, maybe if you did not study chemistry, you don't know that 1 dm equal to 10 meter. And therefore for cube you just do cube on both sides, you find it's 10 to the power 3. And after that you can move on to your usual routine, the ideal gas law. And now what you're gonna do is to remember that I defined it N1 and N2, which represent the numbers of molecules on both sides. And of course, after you open the valve, it doesn't mean the gas will come out here. What it means is the gas can go to each side as long as there are pressure difference. But no matter how you move, the numbers of molecules is still eventually the same. So what happened is by rearranging the PV equals nRT here, you can try to express the before you open the valve. You can express by the equation here for N1 and N2 with respect to their volume and pressure, and therefore you may find N1 and N2, and which would equal to the total amount of course, the numbers of molecule at last, and that will be corresponds to the new pressure that you reach at last as well. And of course, the new volume, you should take all the space, which is 3 plus 6 dm cube. And after you write this algebra equation, you will find your answer. The new pressure is basically 10 times 10 to the power 6 PA, and that's the answer. Next question. Finally, you see for part A, you need to calculate the pressure of gas, and you finally use the first equation you see in the study guide, which is the pressure equal F over A. Pressure for solid that you learn in IGCSE physics. So for the force here, obviously is the weight given by this chunk of mass, and for the area is talking about, of course, on the piston, should I call piston? The cylinder here. That these surface area, and therefore, obviously from the question, they did not tell you, they only tells you the height, which is 0.5 meter, and the corresponding volume, and therefore simply just a simple trick, you'll find the area by yourself using V divided by H, and therefore you'll find the pressure at the beginning to be 9x1 Pascal. For part B, ask you to calculate how many molecules are there. Again, you apply the old trick, the ideal gas law. You put all the things you know, except the fact that you don't know the numbers of molecule, and you find the answer, which is 0.0202 mole. And since they ask you how many molecules, then you simply convert it back to numbers of molecule, which is what you did was times 6.02 times 10 to the power 23, so that you can get how many molecules exactly. For part C, what you need to do is to consider the ideal gas law again. It tells you that the temperature increases, and now you want to find the new volume. So very similar trick that I'm not going to draw everything out again, and you should be able to write this equation. V over T should be a constant, and again you substitute all the things you know. Make sure it's in Kelvin scale for temperature, and you should be able to find the new volume. Next question is more like a break, because suddenly I feel this difficulty drop quite a lot. It's a very simple question. I think you can read it yourself. Next question is again a simple one, and make sure you get the numbers of mole first, and pay attention to the units. It was in kg, so you're gonna times 1000 here to get the correct numbers of mole, and therefore you can apply the ideal gas law. Next question is a longer question, but nothing new. Here are the steps, you can read it yourself. In the next question, I thought I see something new and exciting from the textbook, but I'm wrong, because for the density here, it just apply the simple density equation, density equal mass over volume. In part A, what you're going to do is you apply the ideal gas law, you find the volume, and since you know the molar mass, you know it's 4 gram, mass over volume, you find the density. And I think the only meaningful part that the insight that given from the question is if we revisit and look into the ideal gas law again, it tells you that as long as the pressure and numbers of mole and the temperature are the same, even if they are the different kind of gas, say helium and oxygen here, they would actually have the same kind of volume as well. Got the idea? That means no matter like what kind of least dense gases on Earth or most dense gases on Earth, in ideal gas law, in theory, they should have the same volume as well. And therefore, in your calculation, it's extremely easy because you know the mass is 8 times greater and while the volume is the same. And therefore, the density, what you need to do is just times 8 if you look at the ratio here. In the next question, what you're gonna do is to, giving out a good expression on the presentation. So firstly, in my mind, what I did was P2, well, since the question set is gonna be double, so the P2 and T2 will be the double twice of the original. And then what I start to do is again the ideal gas law. I try to express the volume V1 here with the original temperature and pressure, and of course also the new volume with the new T2 and P2. And now I find that according to the information given here, I find it can be equal to 2T1 and 2P1. And at last, of course, they would cancel each other for that 2 on the fraction. And at last, you just go back to V1, which is a bit disappointing. And therefore, the density is the same. Next question, finally something very exciting, because you can finally use something you learn in IB physics, which is the average kinetic random kinetic energy. Here we only consider one particle only. And very simply, from the equation, from the question, it tells you to calculate the average speed, root mean square speed, and they give you a temperature. Then surely that's a hint that you must use this equation. And if you can write this equation, basically you kill the question. You have done it already. But pay attention to the details that remember this is calculating KE, and if you do remember what you learned in energy, for mass the unit is always in kg, and therefore the mass that you are going to substitute should be in kg as well. And therefore what you need to do is to divide 1000 here. And do remember that the 4.0 here is talking about for 1 mole of helium they have 4 grams, and therefore for 1 helium atoms, then you will only have 4.0 over the Avogadro numbers, which is 6.02 times 10 to the power 23. And for the Boltzmann constant, just substitute into it. Temperature, just substitute again. And lastly, you should be able to find the answer, 2,300 meters per second. Next question, I pretty like it because it does not involve any numbers, and that means you're deriving something new from your own knowledge. So here we go. Again, you start with the average random kinetic energy, which you have proven in the lesson. And this is a kind of very typical combo that you use. You know combo, right? Combo like a combo strike in those like computer games. And after that, what you need to do is you need to change the mass into the bigger mass over Avogadro numbers, so that you can lazily cancel out the Avogadro numbers on each side, so that you can make the owl as requested from the question. Instead, of course, you cannot. Well, you are not going to use the Boltzmann constant KB times T, because this is basically a combination of the R gas constant over Na, which is this is not what we want from the question, and therefore you should do this instead. Anyway, after you rearrange the question, the equation, you can clearly see that's the answer. So you can see that for the speed of molecules, it is correlated with the temperature, and it could be related to the molar mass as well. Okay, so here come the final boss of our exercise. And here is the calculation that I find. For part A, you need to calculate the average random kinetic energy at 300K. So they did not tell you any other information, but still you should be able to find the answer here, which is 6.21 times 10 to the power 20 negative 21 joule, by substituting the T and the KB correctly. Unfortunately, I don't understand why the textbook answer key is different from mine. If I'm not entirely sure, so if you find any mistake that I make here, please let me know. For part B, is something that you need to make use of the previous question, or you can make use of the equation, the combo again. And since you know the temperature is the same, and therefore you can simply apply this combo twice and put one over the other one. So say for the 4 gram mole, that one, which I will be using 4 here, and therefore the molar mass is 4 and the other one is 32, and the temperature is the same, and therefore the ratio is more like this. And therefore is for the ratio, it will be square roots of 8, which is 2.83. And again, it's not the same as the textbook. If you find any, I try to look for any possible reason, but I don't think I make any mistake here. But if you do find any problem, please let me know and I will change that. And that's the end of the video. Thanks for watching. I know it's an extremely long video that it did not happen before because it involves so many questions. I really appreciate you finish it, and I'll see you next time.